This is the first of two sessions where we will be hearing about new research on greenhouse gas emissions and carbon sequestration potential in lower Fraser Valley agricultural systems. Today in part one, we're focusing on vegetable production, and next Tuesday, our presenters will share research on blueberry production. I'm Shauna McKinnon. I'm the coordinator for the BC Agricultural Climate Adaptation Research Network, and I'm pleased to be hosting today's session on this timely topic. And it's great to see such strong participation in today's session. And we have a packed schedule for you for the next 60 minutes. So we're gonna dive right in. As we begin, I'd like to acknowledge that I'm hosting this session today from Vancouver, which is the ancestral and unceded territory of the Squamish, Tsleil-Waututh, and Musqueam nations. And we do have people joining us today from many parts of BC and beyond. And I would like to take a moment to welcome all of you and to recognize the traditional stewards of those lands as well. This is a great time for everyone who is tuning in today to introduce yourself in the chat. ACARN, as a research network, is very interested in building connections, and sharing a bit about where you're joining from and why you're interested in this topic can be really helpful for building new opportunities for partnership and collaboration. So don't be shy, and the other attendees can only see who else is attending once you make a comment in the chat. And when you introduce yourself there, please make sure you send your message to all attendees and panelists. The default option is to just send it to the panelists, and then others can't see who you are. So I'm just going to give a quick rundown of what our hour together is going to look like today. We're going to be starting with Dr. Andy Black, who is a professor in the Faculty of Land and Food Systems, who leads the Biometeorology and Soil Physics group at UBC Vancouver. Andy's going to be providing an overview of the Agricultural Greenhouse Program project that he's been leading the last 4 years. Next, project partner Drew Bondar, Executive Director of the Delta Farmland and Wildlife Trust, we'll be discussing their beneficial management practices programs. After that, we'll have 3 presenters who will get into the details on project results. Ningyu Quan, a recent UBC MSc graduate, will share her research on GHG emissions and carbon sequestration in Delta potato and pea fields. Louis Fausak, applied biology education and research technician in the Faculty of Land and Food Systems, will be discussing the results on effects of short-term grassland set-asides on GHG emissions in bean and potato crops. And Chantel Chizen, a recent UBC MSc graduate, will share her research on the seasonal response of GHG emissions to nitrogen fertilizer inputs on potato crops. And then to wrap things up, Dr. Sean Smuckler, Associate Professor and Chair of Agriculture and Environment in the Faculty of Land and Food Systems, UBC, will be giving an overview of B&P options for vegetable production to reduce GHG emissions and or sequester carbon. So after each of our main presenters today, we will have a short Q&A, just a couple of minutes, and then we'll have a longer period of Q&A at the end of the session. To keep things moving smoothly, I'd like you to type your questions into the Q&A box. You'll find that in your Zoom control panel. And since we have a lot of speakers today, I encourage you to enter your questions as the presenters are talking. And if you can type the name of the person you're directing the question to into your question, then we can more easily direct it to the right person when we get to the final Q&A. If you see a question in the Q&A box that you'd like to see answered, we also have an upvote option. You can use the thumbs up icon right beside the question, and then that will rise the question to the top of the queue. This can be really handy if we do get a lot of questions there, because we'll be answering the upvoted ones first. Also, if we do have a lot of questions, we don't want to cut it off at the 60 minutes. We will be going a little bit longer. So please pose your questions and we'll make room for discussion. And if we don't have a chance to get to everyone's questions, there will be other ways that we could follow up afterwards. Okay, well, let's get going. It's my pleasure to pass things to Dr. Andy Black. And yeah, thank you for providing us with an overview of the project. Thanks, Andy.
Welcome everyone to this week's webinar, and hopefully you'll be able to join us next week as well. We're very excited to tell you some of our results of this research. Let's start by looking at the contribution that agriculture makes to Canada's GHG emissions. As you can see here, Canada's total GHG emissions amount currently to about 710 megatons of CO2 equivalent per year. And the agricultural sector is responsible for 60 megatons of that, and that's about 8.5%. It's a very significant percentage. And importantly to us today is that the agricultural soils account for 25 megatons of that 60. That's 40% of the ag sector, and this is what we're really directing our webinars toward. And an important thing I'd like to point out here, as you can see in the graph, is that over the last 2 decades, emissions from our agricultural soils have been increasing. This is the real concern. And that's really why Agriculture and Agri-Food Canada really came up with the what is called the AGGP program, the Agricultural Greenhouse Gas Program. And our team at UBC was fortunate enough in 2017 to receive funds to carry us through a 5-year research project with the title of Quantification and Mitigation of Greenhouse Gas Emissions from High Value Agricultural Production Systems in BC. So that was our mission, and our promised deliverables, and I think we're doing fairly well on that, are to come up with annual estimates of GHG budgets for major crop systems in the Lower Fraser Valley, and really come up with some beneficial management practices to minimize these GHG emissions, and at the same time, hopefully, maximize crop production and lower the rates of end fertilization. There's our real goals. So you're going to be hearing a lot about these kind of measurements that you're seeing on the screen now. There's basically two kinds that we've been employing. The first is a micrometeorological approach called the eddy covariance approach. And you'll see the instrumentation on the right-hand side here. There's a sonic anemometer and some sampling tubes and so forth. And the important thing about this particular methodology is that it measures greenhouse gas exchange at the scale of a farm field. So that's pretty valuable. We can see an entire field with this instrumentation. The other method is using chambers. This is a very tried and true approach. Basically, we close the lid on a chamber and measure the accumulation of greenhouse gas within the chamber. And from that, we can compute just how much greenhouse gas is coming out of the soil. And as you can see, we have two kinds, the manual kind that's pretty nice because we can move around and select spots that we want to measure greenhouse gas emissions from. And then we have the auto chamber that runs continuously. Finally, all of this work is really helping us in the improvement of the estimation of greenhouse gas emission factors. These factors are very important in terms of estimating the emissions. So our annual estimates of greenhouse gas emissions really will benefit Canada by moving us from the fairly simple tier 1, tier 2 emission factors that tend to be used up to what we call tier 3 higher level emission factors. These are emission factors that are really based on sound measurements coupled with modeling, understanding of the processes controlling these emissions. And in so doing, we can come up with much better reporting on agricultural greenhouse gas emissions to the IPCC. So with that, Shauna, I think I'll hand it back to you.
Great, thank you for that, Andy. Drew, I'm gonna encourage you now to share your screen. And if people have questions for Andy, feel free to put them in the Q&A. We will get to those at the end of the sessions. So next up, we have Drew Bondar, Executive Director of Delta Farmland and Wildlife Trust. And he's going to be talking today about Delta Farmland and Wildlife Trust Beneficial Management Practices programs. Go ahead, Drew.
Thank you so much, Shauna. As Shauna mentioned, my name is Drew Bondar. I am the Executive Director of the Delta Farmland and Wildlife Trust, which is a nonprofit organization that works with farmers in the Fraser River estuary to improve soil health, as well as enhance farmland for wildlife habitat. So for my brief presentation today, I'm just going to quickly talk about the organization and 3 of our stewardship programs that promote sustainable land management. So the Delta Farmland and Wildlife Trust was established in 1993 by a group of farmers and conservationists who at the time were quite concerned with the ongoing loss of farmland that was occurring, as well as ensuring that farmland was being managed in such a way to support the large populations of migratory birds that pass through the region every single winter. And just quickly as a side note, the Fraser River estuary supports the greatest abundance and diversity of migratory birds in all of Canada over the winter season. And as the landscape has changed significantly since the estuary was diked and drained for agriculture back in the late 1800s, many species of birds that inhabit the region have become dependent on farmland for either roosting or foraging habitat as a result, which has made it particularly challenging for many farmers in the region whose fields sustain extensive damage from waterfowl over the winter season. And this is a big part as to why the Delta Farmland and Wildlife Trust was established. So our motto is kind of partners in stewardship. We work very closely with the agricultural communities in the city of Delta and city of Richmond. So we are 100% dependent on local farmers to voluntarily participate and implement our stewardship programs. We offer 7 different stewardship programs, all of which either improve soil health or provide wildlife habitat. Our stewardship programs integrate research, education, and financial incentives. So each program is structured in a cost share where we share in the cost with growers to make it economically feasible to implement these best management practices. We have also been working in very close partnership with various academic institutions since the organization was established, including the University of British Columbia Institute of Technology, Simon Fraser University, to conduct monitoring and evaluation of our programs and to identify the benefits. And then in addition to the research and financial incentives, we do also conduct a lot of outreach to raise awareness about the significance of the Fraser River estuary, both for migratory birds as well as agriculture. Last year, we dispersed roughly $500,000 to just over 40 farmers and landowners in the city of Delta and Richmond, and we're able to enhance just over 4,500 acres of farmland. And since the organization was established, we've dispersed roughly $9.5 million in cooperative cost share payments, which has resulted in the annual enhancement of over 3,500 acres of farmland. One of our primary stewardship programs is our winter cover crop program. And what this program promotes is planting either a cereal, legume, or some sort of grass after the harvest of the cash crop in late summer. Those fields then establish over the next couple of months into this dense kind of vegetative cover, which you can see in that top picture there. And this provides many different benefits, both for soil as well as wildlife. Some of the soil benefits include a reduction in soil erosion due to the heavy winter rains we see here in this region. If it's a legume crop, it can fix nitrogen, it scavenge the soil for leftover nutrients. Over time, it can increase soil organic matter, reduce soil compaction, suppress weeds, improve water infiltration. So a long list of benefits that can result in improved crop yields. But in addition to the soil benefits, cover crops also are equally as important and kind of unique to this region for the value they provide for migratory bird habitat, and particularly migratory waterfowl that extensively foraged on these fields over the winter season, which you can just see in that bottom picture there, which is of the same field above that's been grazed over the winter season to practically nothing left. You just see the tops of tillage radish there. Yeah, every year we have about 3,000 acres enrolled in the program, and we offer a cost share of $60 to $65 an acre to support this practice. Another one of our primary stewardship programs is the grassland set-aside program. And what a set-aside is just simply temporarily removing farmland from production, seeding it to a grass legume mixture, and then letting that field rest from anywhere from 1 to 6 years. This is particularly important as these fields kind of resemble the historical tall grass habitat that existed in the estuary prior to it being diked and drained. And this habitat is very important for many birds of prey, including species at risk that feed on populations of Townsend bull that live in these set-aside fields. In addition, the importance of habitat it provides, it's equally as important for soil health. Set-asides are known to improve soil structure, reduce soil compaction. It can increase soil organic matter over time, improve nutrient cycling, provide habitat for beneficial insects. So we have about 450 to 600 acres that are enrolled in our grassland set-aside program annually, and we offer a cost share of $400 an acre to support this practice. Last program I'm just going to touch quickly on is our hedgerow stewardship program. And what a hedgerow is just simply a linear row of native trees and shrubs that are planted along the borders of farm fields. Number of different benefits as well in terms of sequestering carbon. They act as wind barriers to prevent soil erosion. They provide year-round habitat for an array of different songbird species as well as birds of prey. They act kind of as insectaries as well, providing habitat and refuge for beneficial insects, including pollinators, parasitoids, predatory insects, and all of which can result in improved crop pollination as well as improved biological pest control. So we plant one hedgerow annually, and we cover the cost for full establishment, so including the plant material, planting, we install drip irrigation, and then mulch. And we also cover the first 5 years of maintenance to support this sustainable practice. And since the program was established, we've planted just over 10 kilometers of hedgerows. So I just want to quickly acknowledge our sponsors and funders, of which we would not be able to do the work we do. A lot of these funders have been long-term supporters of the organization, including Environment Canada, Delta Agricultural Society, Habitat Conservation Trust Foundation, Wildlife Habitat Canada, BC Waterfowl Society, both the City of Delta and Richmond, as well as Ducks Unlimited Canada. And
Thank you. Oh, sorry. Didn't mean to cut you off there, but thank you so much for providing that context, which will be really helpful as we're digging into some of the research results. If there are questions for Drew, feel free to put them into the Q&A now. And while we're waiting for questions to get in, Ningyu, you could go ahead and share your screen. The next presenter will be Ningyu Quan. She's joining us today from China, so thank you for joining us. She completed her MSc in Soil Science at UBC under the supervision of Dr. Andy Black. And yeah, if you have questions for Andy or for Drew, feel free to put them in the Q&A. We can always get to them at the end. So in the interest of time, Ningyu, why don't you go ahead and start your presentation? And yeah, Drew, I'm sure we'll have a chance to follow up on some people's questions on that as we get towards the end. Thanks very much.
Thank you, Shauna. Today, I'm going to talk about greenhouse gas emissions and carbon sequestration in potato and pea fields in Delta. So as part of the AGGP project, my research was aimed to make continuous measurements of nitrous oxide, methane, and carbon dioxide fluxes from potato and pea fields in the lower Fraser Valley using the eddy covariance technique, and also to estimate the annual carbon budgets and greenhouse gas budgets of potato and pea crops. So this research was carried out on Rinaldo Farm on Western Island. And the soil on Western Island is glacial soil, and the texture is silt loam, and it's naturally poorly drained and are prone to ponding in the winter. And in terms of the crops, the potato was planted in 2018, and the pea was planted in 2019. And you can see these two crops in the figures. And what we used to measure the greenhouse gas emissions was the eddy covariance system. And you can see this setup in the figure on the left-hand side. And this setup enables high-frequency measurements of wind speed and GHG mixing ratios, which allows continuous measurements of CO2 and other GHG exchanges between the field and the atmosphere, and also enables the determination of the cost of carbon sequestration in the field during the year. And also it can provide an estimate of net change in soil organic carbon if we know the amount of the harvest biomass removed from the field. And next, I'm going to talk about some key results from my research. So let's look at the nitrous oxide flux first. As you can see from this figure, the nitrous oxide flux peaked after the fertilization application for potatoes. And during the non-grown season, you can see multiple N2O pauses because of the frequent rainfall events. So if you look at the cumulative N2O fluxes during the potato grown season, the non-grown season, and the pea grown season, you can see the emissions during the non-grown season was greatly higher than that for the potato grown season and the pea grown season. And the annual N2O fluxes for potatoes and peas were listed in this table. And actually the N2O emission factors for both crops were much higher than the IPCC Tier 1 and Tier 2 estimates. And next, we are going to talk about the methane flux. As you can see from this figure, the methane flux was generally centered slightly above zero. And for both crops, they are methane sources. They are weak methane sources. So again, the methane emissions during the non-grown season was higher than that during the potato grown season and the pea grown season. And for the annual methane fluxes, they were listed in this table. And next, I'm going to talk about the CO2 flux, which we express here as the net ecosystem production NEP. And the positive value means the sink, and while the negative value means the source. As you can see from this figure, in the red squares here, which means the carbon was stored in the field. So the number of the days when the carbon was stored in the fields for potatoes, it was 64 days, and for peas, it was 56 days, and they were similar. And also during the non-grown season, you can see low levels of carbon loss to the atmosphere. So if we deduct carbon removal by harvest from the NEP, we can get the net ecosystem carbon balance, NECB, as shown in this figure. So the positive value means sink, while the negative value means source. So for both crops, actually they gained CO2 from the atmosphere as shown here. But if we take into account the carbon removal by harvest, so for the potato, it end up losing considerable carbon, as shown here. And from the climate change point of view, if we compute the GHG emissions in CO2 equivalents using the global warming potentials of 298 and 34 for N2O and methane respectively, you can see from this figure, even though for both crops, they uptake CO2 from the atmosphere, but because there were large N2O emissions for both crops, so they end up being GHG sources here, shown here. If we consider the carbon removal by harvest for both crops, they end up being a stronger GHG source, which you can see from the last columns. So at last, I want to summarize my key findings. The first one is significant N2O emissions were triggered by frequent rainfall events during the non-grown season. And the non-grown season N2O emissions account for more than 60% of the annual emissions. And the annual emissions for both crops greatly exceeded Tier 1 and Tier 2 estimates. Number two is methane emissions. It was very low and were inconsequential in the GHG budget. And number three was there was net uptake of CO2 by both crops. But if we consider the produce removed from the field, there was a high annual net carbon loss for both crops. And number four is high N2O emissions, especially for the potato crop. It make the fields strong GHG sources. And the last one is beneficial management practices such as cover crops and corrected nitrogen application, like for us, which we say like red source, rate, place, and time need to be developed. At last, I would like to thank Agriculture and Agri-Food Canada, the Renowned Farm, and everyone involved in the AGGP project. And thank you, everyone. And any questions is welcome. Thank you.
Great, thank you so much for that presentation. The Q&A box is on fire. Thanks everyone for getting your questions in there. There is a question for Ningyu, but I think we're gonna start with a question that loops back to Andy. Dr. Andy Black, could you answer a question on the context for this project? What is driving the increasing GHG emissions from agricultural soils?
Thank you. I think the number one thing is increasing amounts of chemical fertilizers. I think that's basically the answer to that.
Great, thank you. And I see that people have put into the Q&A questions for Drew, who is typing in some of the answers there, which is great. You can see in the Q&A box, you can see the answer questions that have been typed in. Drew, I'm going to direct a question to you, and then one to you, and then we'll move on to our next presenter. But please keep putting your questions in there. So, Drew, one of the questions is, how much of a dent are the programs that you presented, or how much of a dent are they creating in making an adequate habitat for wildlife?
I mean, it's a challenge to answer, but we conduct monitoring evaluation of these habitats over the winter season, and we certainly observe significant use. Our grassland set-asides, we compared species at risk use, so short-eared owl, barn owl, great blue herons, as well as other diurnal raptors, and we saw 16 times higher use of those fields than just regular annual crop fields. We've done songbird surveys of our hedgerows as well for a number of years and observed 70 plus species utilizing those habitats. And then winter cover crops, we conduct vegetation surveys as well as waterfowl surveys, and have seen in our survey just this last winter, there was about over 120 fields that were included in the vegetation survey, and over 50% of those fields were grazed extensively by waterfowl. And we just conducted a multi-year analysis as well and found that there was significantly higher use of cover crop fields by waterfowl than all other types of annual crop fields. So quite significant.
Great, thank you for providing some more insight to that. You can feel free to type in some answers to some of the other questions that are in there. And Ningyu, could you give us a little bit more information on what activities can promote carbon sequestration? And is some of the data that you collected indicating what farming practices can be the most beneficial?
Yeah, so in terms of carbon sequestration, so it mainly happens during the growing season when there is photosynthetic activities for crops. So it depends on different crop types. So yeah, we need to consider some management practice which can maybe increase the photosynthetic activities during the growing season. So in terms of the data I collect, for my data, I just measure the potato and the pea crop growing season, and yeah, I actually don't see any like data indicating that promoting carbon sequestration.
Okay, well, thank you for that. And let's move on to the next presenter. Louis Fausak is the Applied Biology Education and Research Technician in the Faculty of Land and Food Systems at UBC. Louis, you can go ahead and share your screen now. He completed his MSc in Soil Science under the supervision of Dr. Maya Kurzik, who's also joining us today as part of the Q&A. So go ahead, Louis, and thank you, Ningyu, for your presentation.
All right. Hi, everybody. Thanks so much for that introduction. Today I'm going to be talking about some of my master's research about how grassland set-asides affect greenhouse gas emissions in potato and bean crops in Delta, British Columbia. All right, so first question has already been answered by Drew. I'm just going to give you a little reminder. So a grassland set-aside is a field removed from annual cropping. It's seeded with grasses and legumes. And in Delta, we have the Delta Farmland and Wildlife Trust that provides the grassland set-aside stewardship program, where farmers can enroll their fields into a cost share program for a period of 1 to 4 years. And this is done with the goals of providing wildlife habitat, improving soil fertility, and transitioning to organic production. So the way that the grassland set-asides do this are through preventing or stopping tillage for those 1 to 4 years, and then the incorporation of the below ground biomass and the above ground biomass during the production of the, or during the growth of the grassland set-aside. So we've had several local studies on grassland set-asides in the Delta area, and they have found that GLSAs can in fact improve soil structure. They can increase aggregate stability, improve soil mechanical resistance, aeration porosity, and can lower the compaction of the soils. We've also found that there is potential for 3-year-old grassland set-asides to increase plant available nitrogen to subsequent crops. However, we have found no increases in total organic carbon, but that leads to our question of how do these GLSAs impact greenhouse gas emissions after incorporation, which leads into my research. So to do this, we set up an experimental plot in Delta, just south of where Ningyu was. So on similar soils, glaciolic silt loam soils. And we did this with the goals of quantifying and comparing greenhouse gas emissions, so carbon dioxide, methane, and nitrous oxide, with several treatments. So we had an annually cropped treatment that was just like normal production, sort of our control. And then we had the same treatment with nitrogen fertilizer applied. And we also had our 2-year-old grassland set-aside that was tilled in with fertilizer applied. So that was all in 2017. We grew field beans and we applied nitrogen fertilizer at a rate of 80 kilograms per hectare. And in 2018, we followed these exact same plots in the same fields. And we tilled in a 3-year-old grassland set-aside and applied N fertilizer there as well. So in 2018, we grew potatoes and applied a fertilizer rate of 100 kilograms of N per hectare. Great, and then this will be some familiar follow-up from Andy as well. So we use the manual gas chambers to measure here. So on the left, we have our bean crop, and then on the right, we have our potato crop. We measured using an FTIR GasMet gas analyzer. We measured the greenhouse gas emissions on the crop row and between the rows to get an estimate of the overall field emissions. And yeah, so these are some of our results for the daily carbon dioxide emissions. So we have our, this will be a repetitive figure, so I'm just going to take some time to explain it here. So at the top, we have our carbon dioxide emissions. And then in the middle, we have our, we have our our air temperature. In the red line, you can see it follows from June of the one year to January of the following year. So we have an increase in temperature, a decrease, increase. So that's happening here. And then as well with that, we have our precipitation. So we have heavier rainfall in the winter. And then on the bottom, we have our soil management. So we have tillage, seeding and fertilizer, side band of fertilizer, and a harvest. And then this repeats. So this is for the beans, and then it repeats itself for the potatoes, a similar soil management. So we can see here that the daily carbon dioxide emissions are higher in the summer, and then in the fall, winter, they're lower. And then in the next growing season, we have that additional 3-year-old grassland set-aside treatment. And we can see that there's more significant differences happening in our 2018 production season with potatoes. and that same increase in carbon dioxide emissions and a decrease in the winter. So it's sort of difficult to tell what total emissions look like here. So we average them for the production and non-production season. So on the left, we have our average seasonal carbon dioxide emissions, and we have the 2017 production season and the non-production season. So bean crop here, and then we move into the potato crop production season, non-production season. We can see that there's no significant differences in 2017 production, non-production season, but once we get into the 2018 season with potatoes, we find that the 2-year-old grassland set-aside and the 3-year-old grassland set-aside increase emissions during the production season. And then we see these results carried over into the non-production season with 2-year-old grassland set-asides increasing emissions, but the 3-year-old grassland set-aside is back to normal. Okay, and then this is moving into our methane emissions. So this is a similar figure to before. We just have methane here, and then we have our precipitation and air temperature and our management again. So we can see on the left-hand side that the scale is much smaller here, and that there's not a lot of significant differences. There's only one day where there's actually significant differences. So when we look at our averages here, first of all, the fluxes are quite small. There's no general trend whether the soils are producing or consuming methane. And there's no significant differences across both years. So this is that same figure, but with nitrous oxide emissions here, and then the precipitation, air temperature, and soil management. So one of the things that we can see here, there are a few significant differences, and then we're seeing large fluxes when there's periods of saturation in the soil. So here's one large flux, and then we're getting another here and here. And when we move into our averages, we're finding that even though they're small, there's still significant differences here. So in 2017 in the bean crop, we found an increase in emissions in the 2-year-old grassland set-aside compared to our controlled annually cropped fields with and without nitrogen. So, and then we move into our non-production season. So when it's rainy, we have increased emissions here with that same trend. So our 2-year-old grassland set-aside is increasing emissions. And then when we move into our 2018 season with that additional 3-year-old grassland set-aside, we're finding some conflicting results here, that the 3-year-old grassland set-aside is actually decreasing N2O emissions, while the 2-year-old grassland set-aside has some legacy effects where it's still increasing emissions compared to our annually cropped with no fertilizer, and higher than our 3-year-old grassland set-aside. And then once we move into the non-production season, we see that there's still that legacy effect on that 2-year-old grassland set-aside, but the other fields have returned back to normal. Okay, so that brings me to our key findings. We found that the 2-year-old grassland set-aside with nitrogen and 3-year-old grassland set-aside with nitrogen seem to increase CO2 emissions. So that is telling us that any potential mitigation from the sequestered carbon associated with the GLSA must account for the emissions in the subsequent seasons and during the growth of the GLSA. Hence, there's a need to quantify what's happening during those GLSA growth periods. And then we also found confounding results for our N2O. So we had the increase in the 2-year-old grassland set-aside, but a decrease in our 3-year-old grassland set-aside. And another important finding is the potential legacy effects of GLSA persisting 1 year after crop production, which suggests that we need to keep following these GLSAs at least 2 years to see how their legacy effects are affecting greenhouse gas emissions. And with that, I'd like to thank my supervisors, my committee members, or my supervisors, Sean Schmuckler and Maya Krzic, and my committee members, and all of the great support I received from everybody in my lab, and all those sponsors as well. And if you have any questions that we can't get to today, you can copy down my email and feel free to send me something.
Great, thank you, Louis, for that presentation. You can feel free to type your questions for Louis into the Q&A. I think we'll get to those at the end of the rest of the presenters. And for now, let's move on to our next presenter, Chantel Chizen. She's going to be sharing her research, which from her recently completed MSc in Soil Science. And Chantel, I'm just going to pass it over to you. And I just want to also say thank you to our presenters who have presented so far, who are madly typing in some of the answers to the questions that have been posted so far. So feel free to keep typing in your questions. And after Chantel's presentation, we can loop back to some questions for Louis, as well as questions for her. So thank you, Chantel. Take it away.
Thanks, Shauna. Yeah, so like Shauna said, I'll be talking about my master's research, and we looked at the seasonal response of greenhouse gas emissions to different nitrogen fertilizer inputs in a potato crop. So the project objectives for this research project was to evaluate the relationships and trade-offs between inorganic nitrogen fertilizer rates, we were applying urea, as well as the greenhouse gas emissions, looking at carbon dioxide, nitrous oxide, and methane, as well as potato yield. Other sub-objectives we had were to assess the impact of a 3-week delayed planting on greenhouse gas emissions compared to a regular planting time. So with this, instead of planting commonly at the end of May, the potato crop, we waited 3 weeks and planted it in mid-June, just to see how that would have an effect. And I'll talk a little bit about that later. And then lastly, to consider how the temperature and soil moisture really contribute to the seasonal pattern of soil greenhouse gas emissions in the Fraser Valley. And we looked at this objective through an incubation experiment in the lab. So some background for nitrogen fertilizer rates in the Fraser Valley related to potato production. So in 2018, the reported rate was about 120 kilograms of nitrogen per hectare. And this is higher than the 1990s average rate of 90 kilograms of nitrogen per hectare, and as well the current recommended rate by the BC Ministry of Agriculture at 70 kilograms of nitrogen per hectare. And so these were all reported for potato production in the region. So for my project, we measured greenhouse gas emissions, again, using the gas mat like Louis had used. And we measured every 2 weeks in 2 fields. And one field was considered productive, while the other field was considered unproductive because it had existing issues related to soil compaction and soil salinity. And we had known that it had a hard time producing crop biomass in that field. So we looked at these 2 fields and measured the greenhouse gas emissions from each of the different nitrogen fertilizer rates. So here's a look at our first graph, and I'll walk you through this one because we'll see similar ones throughout my presentation. So here we have the cumulative CO2 emissions. And so in this graph, how it's working is that as we go through over the growing season, this is becoming the cumulative, and here at the end would be the cumulative emissions for the whole growing season. And for each of the different fertilizer rates, the high nitrogen fertilizer rate of 120 kilograms per nitrogen hectare is this dark line. And you can see that with CO2 emissions, that it has the highest CO2 emissions by the end of the growing season in November, and that the control and the moderate have similar ones. Looking at methane, so methane, again, similar to what Louis had found in his potato fields, it was around near zero and there was no really major differences. After harvest, there was a lot of similarity in the end of September, but as we moved into October, November, we saw there was some increase in methane emissions as the soil is getting wetter with our usual rainy periods happening October, November. So we saw an increase in methane emissions with our high nitrogen fertilizer treatment. And for N2O emissions, a similar pattern. And when we applied the fertilizer at planting, we could see the high nitrogen fertilizer rate start to result in higher nitrous oxide emissions, while the moderate and the control of zero remained fairly similar to each other. Again, after harvest here in September, end of September, we saw a further increase in nitrous oxide emissions as we get into that rainier period in October, November, which we refer to as the shoulder season. It's kind of after harvest and it's moving into that shoulder season of the growing season. So one thing I wanted to point out of how we saw that increase, especially October versus November. So this is looking at the cumulative N2O emissions for the whole growing season, but this is on the left is with an October end date, so right after harvest. And this is looking at the difference with a November end date. So I'll say that I talked about having a planting date and how we delayed planting time by 3 weeks. And with that 3-week delay, we were expecting that maybe we would miss some of the wetter spring conditions by planting later in June because the soil still has some moisture, and moisture is a big driver of nitrous oxide emissions. But we didn't see, so we saw that the planting date didn't have a major effect on greenhouse gas emissions, but what did was leftover fertilizer in the form of nitrate that was left in the soil after harvest. So we see here with the November end date, with the 90 and 120 kilograms of nitrogen that was applied, we see a large spike in the cumulative nitrous oxide emissions. And that spike matches with nitrate, soil nitrate that we measured in the soil at these same times. Since we saw that that soil moisture has a really large effect, that's where we see in October, November, those increases in nitrous oxide. We dialed down that understanding into an experiment where we had 4 treatments. So we had a winter temperature, and I'll walk you through this here again. So we had a winter temperature of about 4 degrees, a summer temperature that was 21 degrees, as well as a low soil moisture. So that would be common in July, August that you'd have in the growing season, and a high soil moisture that was representative of maybe a wet spring or in the fall once it starts to rain. So you can see here that these nitrous oxide emissions at a low moisture are near zero. They're all fairly consistent regardless of how much nitrogen fertilizer we apply. And same thing for if it's winter temperatures. If it's too cold, we didn't see nitrous oxide emissions. There's this sweet spot though of kind of the summer temperatures at 21 degrees as combined with that high soil moisture, and that's where we see that increase in nitrous oxide emissions. And the understanding that temperature and soil moisture is well known that it's a control on nitrous oxide emissions. But looking here at these soils from the Fraser Valley, we can really see that fine textured soil. We can see that there's that high increase in nitrous oxide emissions, especially with this 120 rate that's commonly used compared to the 90 and the 0. So we can see that the 90 kilograms of nitrogen per hectare is an opportunity to reduce our nitrous oxide emissions. But the trade-off with that is how does that affect the potato yield? We'd expect that with more nitrogen fertilizer, we'd hope to have higher potato yields, and that's what a lot of producers are anticipating. So looking at our potato yields for 0, 90, and 120, the 90 and 120 were actually quite similar and not statistically significantly different. But we found that that extra nitrogen fertilizer to get you up to 120 kilograms, the cost of that input of that extra fertilizer doesn't outweigh the revenue you get from the added costs of the higher yield. And so this was in that productive field that I talked about, but we also had this unproductive field, and that's the one that had, like I said, the degradation issues. And in that field, we saw that no matter how much nitrogen fertilizer rate up to that 120 kilograms, we didn't see a change in potato yield. And so that was another interesting opportunity that even though this nitrogen is being applied to the field, it's likely not being utilized by the crop. So we don't get a higher yield. And so it's either being lost to the environment, either to the atmosphere as a nitrous oxide or to our water sources. So the key findings is that greenhouse gas emissions, they did not significantly differ with nitrogen fertilizer rate during the growing season. So from that planting to harvest time. However, and also the planting date did not also affect the greenhouse gas emissions or the yield, but there was an increase in nitrous oxide emissions and a little bit in CO2 emissions in November, or in methane emissions, sorry, in November. And this is caused by that combination of leftover soil nitrogen from fertilizer that was applied at planting, as well as kind of the warm, cool temperatures we have in the fall and the high soil moisture content. And so, like I said, that higher yield between the 90 and 120 kilograms of nitrogen per hectare did not outweigh the additional fertilizer costs. And at the unproductive field, the yield didn't increase at all with the increased fertilizer inputs. So the best management practices and kind of the key takeaways from this research is that to reduce nitrous oxide emissions, of course, avoid applying nitrogen fertilizer in the wet spring conditions, and then using a nitrogen fertilizer rate that minimizes the amount of soil nitrogen that is left over after harvest. Also, using this nitrogen fertilizer rate of 90 versus 120 kilograms nitrogen per hectare can reduce nitrous oxide emissions as well as input costs for farmers. And fields with soil degradation should have minimal or low nitrogen fertilizer input, since crop yield is limited by other factors like compaction or salinity. And this is an important opportunity to lower the N2O emissions in the region. And with that, I'd like to thank my supervisor, Maya Kurjic, as well as the rest of my supervisory committee and all the support and volunteers and the AGGP group that helped with my research. Thank you.
Great, thank you so much, Chantel. If you have questions for Chantel, please put them in the Q&A. Right now, though, we'll go to our final presenter, and we will extend the session beyond the hour, so we'll have a chance to get to some of the questions. There's a lot of great questions in the Q&A. So Sean, you can go ahead and share your screen now. Some of the questions that are already in the Q&A, I think they'll probably fit best at the end anyways. Yeah, and if you have questions for Chantel, just put them in the Q&A. Great, and now go ahead, Sean.
Great, thanks, Shauna. So I'm going to end the session with an overview of some of the beneficial management practices, the BMPs that we investigated for vegetable production, and to put them in context in terms of the overall potential if we were to do some rough calculations on extrapolating them out to vegetables across the province. So when we look at our agricultural sector emissions, we're somewhere around 3,000 kilotons of CO2 equivalent emissions. Kilotons is 1,000 tons or 1 million kilograms of CO2e. If we were to adopt as a sector the 40% target by 2030 that the province is taking on, we would aim to be 40% below 2007 levels. So a little more than 1,000 kilotons of reduction. So that could be our goal if we were to get into that to the target game. But that would require a substantial and very rapid decrease in agricultural emissions across the province. So let's look at what our BC vegetables are doing in terms of emissions. So in 2018, we assessed that there were about a little more than 7,000 hectares of vegetables in production, including potatoes. And when we apply a nitrous oxide emission factor of 1.6% of applied nitrogen, we're ending up with about a little more than 3 kilotons of nitrous oxide emissions attributed to vegetable production across the province. So what that doesn't include is emissions related to carbon dioxide coming from soils. So as Ningyu pointed out in her analysis, that we're actually losing carbon from our soils. And this was corroborated by an analysis by Sid Paul, a PhD student that worked with us in 2018. So Sid and a crew did an analysis of soil organic carbon across the lower Fraser Valley. And using both field sampling, satellite imagery analysis, and GIS, Sid estimated changes in soil organic carbon from 1984 to 2018. And what Sid showed was that across the landscape, we see declines in soil organic carbon across 61% of that landscape, which would be equivalent roughly to 2 tons of CO2 per hectare per year. So that's quite a substantial amount. And if we applied that to our 7,000 plus hectares of vegetables, we would increase emissions enormously, almost to 20 kilotons per year. So what we're looking for is beneficial management practices that are going to offset those emissions. So Ningyu mentioned the 4R nutrient management approach. So right source, right rate, right time, and right place. So we ran a trial looking at organic nutrient management in 2 locations, at the UBC farm and at Green 5 farm out on Vancouver Island. And this research was led by Dr. Kira Borden and assisted with by Carson Lee, the project manager. And what we looked at here were options for reducing emissions. We compared a control, no compost, typical applications that would incorporate 1 or up to 3 of the R's, and then a target nitrogen compost application rate, which would be basically 3 of the R's, and then a final target of nitrogen and phosphorus that would be a 4R approach. And what we see over the 2 years that we ran this trial at the UBC farm was that we had significant differences in terms of the typical application rates and the target N plus P, the 4R treatment. And those reductions in terms of nitrous oxide emissions ranged from 24 to 28%, depending on the year. And if we extrapolate that out across all the vegetable area, we would get almost 1 ton per 1 kiloton of CO2 emission reduction. So another BMP that we investigated that had been discussed previously is the winter cover crop and grassland set-asides. We worked with the Delta Farmland and Wildlife Trust and looked at fields that they'd been managing since 1993. And we compared fields that had winter cover crop plus grassland set-asides to fields without any BMPs. And Jordy Kersey is working on this analysis right now and is finding some really interesting results showing that with cover crops alone, we're not seeing significant differences from the fields without BMPs. It's only when we have both winter cover crops and grassland set-asides in combination that we're seeing these significant differences, both at the 0 to 15 and 15 centimeter depth in terms of soil organic carbon. And the difference is substantial, a 43 to 48% difference depending on the depth. And if we again extrapolated that out, assuming those emissions of the analysis that Sid did, we would be getting close to, again, a 1 kiloton emission reduction for vegetable production. And finally, we're going to look at hedgerows and woody riparian buffers as a BMP. This research was led by Lindsay Dowell, a master's student that finished in last year. She looked at the soil organic carbon and woody riparian buffers and both high diversity and low diversity hedgerows and compared that to cropland without BMPs. And again, we see that there's a significant difference in the high diversity hedgerows compared to annual cropland at the 0 to 15, but not at the 15 to 30. But we see substantial differences in carbon when we incorporate that above ground biomass. So this is showing the soil carbon plus the above ground biomass. And in total, we're seeing a 18 ton CO2 per hectare per year reduction in emissions. So if we extrapolated this across all of the vegetable production, we would get more than 2.5 kilotons of CO2 equivalent emission reductions for vegetables. So just to summarize what we found, so in this graph, I'm showing the vegetable emissions just from nitrous oxide, and then the 3 BMPs together and at 3 different rates of adoption. So at a 25% adoption, 50% adoption, or a 100% adoption. And at 100% adoption, we more than offset our annual emissions. So to conclude, we do see that vegetable BMPs are showing promise for meeting emission reduction targets. There are some key caveats to the extrapolation that we've done here. So there's some pretty large, I would say huge assumptions in this analysis right now. There's certainly some large uncertainties, and it's really critical to get better assessments of what the adoption potential would likely be for these BMPs, and then to really target that maximum adoption potential. And then finally, we really do need to integrate some of the other analysis from Chantel's results about the impact of moisture and irrigation, Lewis's results showing the incorporation of GLSA, and Ningyu's results that are getting us a much finer resolution emissions factor. And then going forward, we certainly need to investigate other BMPs that could be applied to vegetable production. Reduced tillage could show some promise, the incorporation of biochar, incorporating green manures as, say, a summer cover crop, or installing tile drainage to better manage soil moisture, particularly on the shoulder seasons, and to enable farmers to get better cover crops established. So I'd like to thank numerous collaborators, particularly the farmers and students that were involved in this work, and of course a whole suite of funders that were essential. And I will open it up to questions.
Great. Well, thank you, Sean. We are at a couple minutes after the hour, but all of our presenters have agreed to stay on. So if you can continue to stay on with us, that'd be great. Please post questions in the Q&A for Dr. Sean Smuckler or for any of our presenters so far. I do want to loop back to a question that was posted in the Q&A earlier for Ningyu. And the question was around whether it's more worthwhile to focus on carbon sequestration, or should we be putting more of an emphasis on just reducing nitrous oxide emissions? Would that be more effective if we're looking at reducing the GHG footprint overall? So Ningyu, do you want to take a stab at that question? And if other presenters would like to also weigh in, you're welcome to do that.
Yeah, I think this is a very good question. But I think because the N2O has a very large climate change impact, because the global warming potential for N2O is like 298. So I think it's definitely very constructive to reduce the N2O emissions. But I do think there might be some cases that if we reduce the N2O emissions, then the carbon sequestration might also be reduced. So it depends. It depends on the magnitudes of the N2O and the CO2 fluxes, which differ among different ecosystems. Yeah. I'm not sure if this answers the Jim's questions.
Thank you for providing your answer on that. Also, I just wanted to mention that we have Dr. Paul Giselle and Dr. Maha Kuzik joining us for the Q&A as well. I don't know if either of you the two of you would like to answer that question, or just add your own comments to some of the questions and presentations so far.
I think most of our efforts are needed to control N2O emissions, and that will also benefit in increasing nitrogen use efficiency and crop production. When it comes to carbon sequestration, my opinion is that agriculture is about growing food and growing food profitably. So what happens normally, we turn up removing more from the field than is fixed in photosynthesis. So increasing carbon sequestration in agriculture in the field is pretty difficult unless we follow start adding more manure or amendments and leave maximum crop residues and follow other BMPs like Sean was telling about cover crops and other amendments. Efforts need to be focused more on decreasing N2O emissions.
Just wrap up with a couple of final questions here. And Sean, I think I could direct this one to you. It's around the use of cover crops, and obviously the intense rain and the length of rainy periods in the Fraser Valley is a contributing factor to emissions. There also have been some questions around drainage issues and how that's contributing. But could you speak to the role that cover crops could play in preventing emissions related to either rain or some of the drainage issues?
Yeah, I think cover crops are a really important BMP to investigate, but many of the farmers that we work with really struggle to get cover crops either established because of the fall rains, or if established, they often get decimated by migrating waterfowl. So we really need to work on strategies to enhance how we are producing cover crops. And tile drainage could be one of them. I mentioned that before as a potential BMP that we should investigate, given that tile drains could help us manage for that moisture and enable farmers to perhaps get a cover crop more effectively established in the fall. And I agree with Paul that it's critical that we immediately reduce our emissions, focusing on the N2O. SID's work showing that the substantial decline in soil organic carbon is really concerning, not just because of the emission implication, but also because of the soil health implication. So to keep our farms producing sustainably in the long term, we have to maintain soil organic carbon. And cover crops are a key way that we can do that. So we need to continue to work on this issue in this region and make sure that farmers can get a cover crop established more effectively.
Great, thank you. I also want to make a clarification that someone raised in the Q&A around what is a BMP? What are you talking about? And that's a beneficial management practice, in case you missed the spelling out of that acronym. Maybe just one final question here is around something that actually goes beyond the research that you're working on. For greenhouse production in the Fraser Valley, is anyone looking at GHG emissions from that type of production?
We've been doing some analysis trying to put in perspective the GHG emissions from greenhouse production. And although per unit area, the emissions are quite high, overall it's a fairly small footprint relative to the total agricultural area in the province.
Well, we're going to wrap up here. I want to thank everyone for participating today. I would highly encourage you to join us next week when we're discussing blueberry production and GHG emissions and carbon sequestration in those production systems. Also, a huge thank you to all of our presenters today. This work that you're doing is so important and providing much needed information on understanding what the GHG emissions are from these types of cropping systems and what are some of the best practices for lowering those emissions. So thank you so much. We had a really active Q&A box, so I will be pulling together those answers that were typed in as well and sharing those with everyone that participated today. And yeah, just thank you very much for joining us, and thanks to those that stayed on a little bit extra longer to continue the discussion. So thanks everyone.